All right, good morning, everybody. Now we're going to finish up chapter 3, looking at inverse trig functions. We first started, well, in trigonometry and pre-calculus, you discussed the trig functions and their inverses. Well, here, what we do, instead of calling them the inverse functions, for example, if we had this equation, sine inverse of x, we would typically write the arc sine of x, right? And remember what inverses are. Algebraically, if we had the inverse of this linear equation, graphically, crosses at 2, up 3 over 1. There's that graph. Now the inverse, the way you find the inverse is switch your x and the y's and solve for y. 3y equals x minus 2 and divide by 3. And that's our inverse. So we'll relatively do the same thing. So this graph turns out to be that linear function. So we cross at negative 2/3, and it's up 1 over 3. So basically what we're getting to is inverse functions are symmetric about that diagonal line y equals x. No difference with the trig functions. For example, if we had cosine of x, the graph of the cosine of x, its amplitude is 1, negative 1. Negative pi over 2, pi over 2, pi, negative pi, 3 pi over 2, negative 3 pi over 2, negative 2 pi over 2 pi. So cosine at 0 is 1, at pi over 2, and negative pi over 2 is 0. At pi, it's negative 1. At negative pi, it's negative 1. And we keep on going to the same graph. So we see it's cyclical. So the domain and the range. Domain is all real numbers, and the range is from negative 1 to 1. That's for our function. But the inverse function, the domain and ranges change. Because remember, we switched x and y. All right, so what the inverse function looks like cosine. So now we go from negative 1 to 1, And we do the same graph, but vertically. Yeah. Instead of having to derive each of these, what um, we're looking at now is just what is the formula for it. Note also that if we do a composite function, or the cosine of the inverse cosine is equal to x, because there are inverses, and that's a property from algebra. If they're truly inverses, then the composite function of them becomes just x. Let's see here. And let's jump straight to example one. Now there are 6 different types of inverse functions. Inverse of sine, inverse of cosine, inverse of cosecant, inverse of secant, inverse of tangent, and the inverse of cotangent. Now, the reciprocal functions, for example, everything goes to sine and cosine. Secant, for example, is 1 over cosine. But since we're taking the inverse of it, then our relational comparison is like that. Cosecant is 1 over sine, so it's the inverse of sine 1 over x. Because instead of writing 1 over sine x, sine inverse of x, we write sine inverse of 1 over x. And tangent and cotangent are sine and cosines, respectively. Now, the problem with this, with some of these formulas, is they don't always give us a set solution, because remember, it's cyclical. So if I say that I want an angle to be positive or negative, if it's positive, greater than 0, or if it's negative, if the angle is less than 0, then it all depends what we have here. So we have a positive y or a negative y, and the x values are the same. That's with the regular function. But what changes now is when we do the inverse, the x and y changes. So x is going to be negative x and positive x for the same value of y. That's traditionally. Now, remember how inverses find. Inverse functions find the angle of a given value. Remember, original functions, if I gave you sine of pi over 4, that's square root of 2 over 2. But if I give you the inverse sine of square root of 2 over 2, then that gives me pi over 4. No, then this will come into the problem, is because there are two places where the sine equals square root of 2 over 2. One's at the first quadrant, and one's at the second quadrant. So we'll have two different angles there. Let's look at example 1. Let's look at the function inverse tangent of x. The inverse tangent of 1 over radical 3. Remember, you can't have rational on the bottom, so we have to rationalize it. A radical on the bottom, so we have to rationalize it. So it's just square root of 3 over 3. So now what we're looking for is, what is the angle that makes tangent equal square root of 3 over 3? Pi over 6. So how did that, where did we get that? Where did we get this information? Remember, this is every triangle is defined by sine and cosine. Sine values define the y value. Cosine values define the x value. So in other words, every point we have on the curve is made up of cosine some angle, sine some angle. So if the radius of this is 2, that's what it says. Remember, tangent is sine over cosine. Sine is opposite over hypotenuse, and cosine is adjacent. So tangent is opposite over adjacent. Here's the angle, the opposite over adjacent. And that equals pi over 6. What if we do the same thing now on the lower half? Well, let's test this. Tangent at pi over 6 is 1 over square root of 3, which is square root of 3 over 3. With the same angles there. Okay, let's look at this same angle, but now a reciprocal of it. Let's get the tangent inverse of negative radical 3, which is radical 3, which is radical 3 over 1. Remember, it's opposite over adjacent. So its angle is negative. Here's your angle. So opposite is negative radical 3. Adjacent is 1. 3 squared. Square root of 3 squared is 3. 1 squared is 1. 3 plus 1 is 4. Square root of 4 is 2. We use quadratic formula for that. Or Pythagorean theorem, sorry. Okay, so we're saying here that this value, since it's a negative, the tangent is sine over cosine, and in the fourth quadrant, cosine is positive, sine is negative. So that means the answer is going to be negative. Tangent of negative pi over 3 makes it negative. I mean, radical 3 is pi over 3, but that's how I always remember it. So let's test it. So if we do tangent of negative pi over 3, that equals negative radical 3. I mean, they're just inverses of each other. And actually this on the sheet I gave you last time for the inverse functions. If my x is radical 3, the angle, in other words, if we did another one, if we had another angle here, we have tangent of this value. I'll call that y. So the tangent of y is radical 3. Tangent of pi over 4 is 1. Tangent of pi over 6 is radical 3 over 3, or 1 over radical 3. Negative pi over 6 is negative radical 3 over 3, or negative 1 radical 3. At negative 1, it's negative pi over 4. So the tangent of negative pi over 4 is negative 1. Tangent of negative pi over 3 is negative radical 3. Yeah, so all the stuff's in there already. All right. Remember earlier in our chapters, we had the inverse function, and we took a derivative of it. From theorem 3, we got this function, the derivative of the inverse function of x. So let's see if sine y over x. Remember, it also extends to u du type stuff. Okay, so our inverse, well, no, our function is just sine x. Then the inverse function is negative x. We're doing the sine function. So what we have here is 1 over. What's the derivative of sine? Cosine x. So the outside is cosine, and the inside is the inverse function. So we have to use cosine u, because we have to expand it. So what we have here is this. We have 1 over cosine u. where u is the inverse of sine. Right. So now how do we expand? Cosine u, remember, cosine squared plus sine squared equals 1. That's the identity. So let's solve for cosine. Subtract sine squared. So we have cosine squared u equals 1 minus sine squared u. Square root both sides. Cosine u is equal to the square root of 1 minus sine squared of u. Just using the basic identity. We have 1 over cosine is that square root of 1 minus sine squared u. Remember, our u function is, we'll open that in a second. Yes, so now we'll do the inverse of that. So this will make, instead of u, we'll put sine inverse of x. What is this going to become? Sine squared x, oops, sine squared inverse sine, that becomes x. Well, not squared, because the inverses of these. So what we have here then, if that's a sine equals x, then 2 of those will become 1 minus x squared. Because if one of these is equal to x, then if I square it, I get x squared. So that's our derivative of the sine function. So here's our first formula. The derivative of the inverse sine of u dx is equal to this. 1 over 1 minus u squared du dx. That's the formula we'll be using. All right, so let's look at example 2. Example 2. What does it say? Using the chain rule, we calculate the derivative. Dx sine of inverse x squared. Using what we found earlier, over square root of 1 minus x squared dx. So in this one, this is our u. So it becomes 1 over 1 minus x squared squared. Because that's our u. Times the derivative of our u. Times 2x. Which becomes 2x over square root of 1 minus x to the squared squared. That becomes 2x, 1 minus x to the fourth. That's our derivative. Let's do one more derivation, and then I'll show you the formulas. And that's all we really have to use. dy dx of tangent u. Again, the theorem 3 that's going to be our saver. Derivative of the inverse f of x is equal to 1 over f prime f inverse. We'll be using this pretty much all the time. And we know because the domain of the tangent function is negative infinity. No, the domain is the periods, which are negative pi over 2, and it goes up because the tangent function looks like this, where it has asymptotes at negative pi over 2. So the period is pi. All right. So using this formula, the derivative of this one will be the derivative of tangent secant squared. So we get secant squared times the inverse function. Remember, this is our f of u. Our u is tangent inverse of x. So this is the derivative f prime of that. Just make it easier to see, like that. Okay, and the identity functions. Remember, we had cosine squared x plus sine squared x equals 1. Secant is 1 over cosine. So if I divide by everybody by cosine squared x. I get 1. Sine over cosine is tangent squared. 1 over cosine is secant squared. So secant squared becomes 1 plus tangent squared of u. Now, why did we do that? Because u was tangent. So we have tangent squared, u is the inverse tangent, x. Well, the tangent and the inverse tangent, tangent squared, or tangent inverse tangent of x is equal to x. So what this one becomes is 1 over 1 plus x squared. That's particular to this one. Oh, since we start off with du, tangent u, so that's got to be u, and that's got to be u times du dx. So we start off with u already. But that's the formula using that. It's whatever u is, find the derivative of it, and then plug it in there, and find the derivative, put it in there. Okay, this is the same logic, same concepts go for secant, cosecant. Let's look at example 3. Using the chain rule and derivative of the using the chain rule and derivative of the arc secant function. Find the derivative of the inverse of secant of 5x to the 4. Yeah, typically we don't write that. We write that, but that's when is the inverse function. All right, so we're looking for this. We're looking for the derivative with respect to x of the inverse of secant of 5x to the 4. Well, u is 5x to the 4th, so du dx is 20x cubed. On the last page of your sheet, there's the derivative of the inverse of secant. So we get the absolute 1 over the absolute value of u squared minus 1 du dx. So the derivative of secant inverse of u is equal to the 1 absolute value of x, square root of u squared minus 1 du dx. All right. So let's just plug it. We know what EU is. So our derivative is 1. This is U. So it's absolute value of 5x to the fourth U squared, which is 5x to the fourth squared minus 1 times the derivative, which is 20x cubed. X cubed, 5x to the fourth, and 25x to the eighth minus 1, because we distribute that. Now, question, do we need the absolute value sign here? We'll just split that up into 2 parts. 5 is a constant. It can never be negative. So, and x to the fourth is always positive. So we really don't need the absolute value signs for 5x to the fourth. And this is 25x to the eighth minus 1. And just clean, so 3 gone, so that one's all but 1's gone. 5 goes into 24 times 4 over x, 25 x to the 8 minus 1. And there's your answer. So again, you can use these formulas back here, the derivatives of inverse trig functions, because the derivation of all of them are all the same procedures. Well, no, this last part is pretty important because it helps us to rewrite things as needed. Inverse cofunction identities. For example, the inverse of cosine is the same thing as pi over 2 minus inverse of sine x. The inverse of cotangent is pi over 2 minus the inverse of tangent of x. And the inverse of cosecant of x is pi over 2 minus secant x. So that gives us, actually, we could find all 6 of them. Give you 3 of them here. You could find sine, move that over, change the sign. So the sine, inverse sine x would be pi over 2 minus cosine. Tangent would be pi over 2 minus cotangent. Secant, so we just drive those. And these just make it easier to help us find, solve equations. Let me see if there's an example. Example. Find derivative of the cosine function using what we just have up there. So we have the derivative of the inverse cosine of x dx is equal to the derivative inverse cosine is pi over 2 minus sine inverse of x. We distribute, so we have dx of pi over 2 minus dx of sine inverse of x. Remember, we use the sum rule or difference rule. The derivative of a constant is 0. So we have the derivative of the inverse of sine. Well, the derivative of sine is 1 over 1 minus u squared du. So it's 1 over, it's negative, I should say. 1 minus x squared. Since this is our u, du equals 1. So it just equals that. And that's all there is to it. Just use the charts. All right, that does it for that section. Actually, does it for that chapter. Next week, we will start chapter 4. And chapter 4 is going to be the long one. Once we finish chapter 4, chapter 5 should go pretty quick. All right, everybody. Have a great, safe, long weekend, since you don't have to see me till Monday. And I'll see you in class Monday. Or see you online on Monday.